Hello, welcome to my talk. My name is Peng Liao. I'm currently a postdoc at Harvard University. Today, I'm going to present a project on how we design a reinforcement learning algorithm for use in a physical activity study called HeartSteps. I'm going to start with a brief introduction. Mobile health intervention becomes a fast-growing field in the recent years due to the technological advancements. This allows us to not only collect data in real time, but also deliver interventions anytime and anywhere. The goal of the so-called just-in-time adaptive interventions, or JADIs for short, is to use the real-time collected information to inform the delivery of the right interventions at the right moment to help the users to achieve their health goals and maintain the healthy behavior. In this work, we develop a reinforcement learning algorithm. So what is reinforcement learning? Reinforcement learning is a sub-area in machine learning. The goal of the reinforcement learning is to learn how to best select the actions to maximize the total rewards while interacting with the unknown environment. Um, this work is motivated by our collaboration on HeartSteps. HeartSteps is a physical activity mobile interventions. There are many intervention components in HeartSteps. Here we focus on the walking suggestion message. Our goal is to design a reinforcement learning algorithm that decides at each decision time whether or not to send the walking suggestion message in real time to help the individual increase their physical activity. Here's the figure representation for the study design. During each of the 90 days in the study, there are 5 user-specified decision times uh, in a day. If the user is currently available for receiving a message, the RL algorithm uses the current context as well as a summary of the past history to determine the randomization probability for sending the message. After the 5 decision times in a day, the algorithm updates the treatment policy using the information collected throughout the day. We identify a few key challenges that need to be addressed before applying the R algorithm to optimize the mobile health intervention. First of all, many online reinforcement learning algorithm requires the agent to interact many times with the environment before starting to perform well. This is impractical, especially in mobile health application, because the user could lose interest and disengage quickly. Uh, so the R algorithm should learn quickly. Uh, Secondly, uh, due to the complexity of the context space and the unobserved aspect of the user's context, the observed human behavior is often complex to model and exhibits some level of non-stationarity over a long period of time. As a result, the algorithm should accommodate some model misspecification and non-stationarity. Uh, the mobile intervention often tend to have a positive effect on the immediate reward. On the other hand, intervention likely produce negative impact on the future rewards due to the habituation and burn. So it's critical for the algorithm to adjust for the longer term impact of the current action. Lastly, we want to ensure that after the study is over, the data can be used to conduct causal inference to test and develop new behavioral science theory. Uh, we want to ensure that those analyses are feasible. We develop a reinforcement learning algorithm to address these challenges. At the high level, there are 4 main components in the algorithm. The algorithm is built upon a Bayesian low-dimensional linear model for the reward, and we use informed prior based on a prior study. We develop a trick in estimating the posterior distribution called the action centering to protect against model misspecification and non-stationarity. To adjust for the possibly negative delay effect of sending the message, we design a dosage variable of using the discounted sum of the past treatment and use the dosage variable to form a low variance proxy of the future rewards. Finally, the actions are selected stochastically akin to a Thompson sampling, and we restrict the minimum probability of selecting each action away from 0. This ensures the feasibility of the causal inference and of policy learning when the study is over. The key takeaway for this presentation, in this work, we developed a reinforcement learning algorithm for use in HeartSteps V2. The preliminary validation of the algorithm demonstrates that it outperforms the standard Thompson sampling banding algorithm in the simulation. We also assess the performance of the algorithm using the pilot data from HeartSteps V2, which shows some initial good signs of the algorithm. The HeartSteps V2 study is not finished. We are currently working on the data export and planning to further assess the performance of the algorithm. In this work, the algorithm uses the user's own data to learn the treatment policy. A very important direction for future research is how to properly and efficiently combine the data from all the participants to further speed up the learning process. This is the end of the presentation. Thank you for listening.